Okay, so let me start with the introduction. It's a great pleasure to have Jens Marklof from Bristol University as our distinguished speaker. In fact, Professor Jens Marklof, FRS. So Professor Marklof has graduated in 1997 with a PhD from Ulm University under Frank Steiner. After a short postdoctoral period, he was appointed as a permanent faculty in Bristol University in 1998, where he is currently a full professor and the Dean of Faculty of Science after serving a term as the head of school. The research of Professor Marklof is broad and deep, though the official title is Professor in Mathematical Physics. He specializes also in quantum chaos, dynamical systems, number theory that includes modular forms, equidistribution, analytic number theory, and other related subjects. You will see it all today. For his excellence in research, Professor Marklof has won many prizes and awards. Let me give a partial list. The reason it's partial is because the alternative is either to listen to the list or to listen to the talk. And I think we're going to talk for the forum. So the partial list is Whitehead Prize in 2010. He was elected, as already mentioned, as a Fellow for our Society, 2015. He was awarded the ERC Advanced Grant, a number of EPSRC, Liverpool, and Royal Society fellowships. And he was also a speaker at ICM 2014 in school. Professor Marklof is the next president of the London Mathematical Society. So with no further ado, I'm going to fulfill my promise and let you speak. The title is Random Lattices and their Applications, from statistical mechanics to numbers.
Great, thank you very much, Igor, for this very kind introduction. Thank you all for coming to this colloquium. It's really nice to be here. So I hope this will be relaxing and entertaining. Please interrupt me if you have any questions. So I'm going to talk about random lattices and just mention a few applications, a number theory, statistical physics, geometry, so a variety of areas. So to motivate the notion of a random lattice, I'm showing you here two point sets. One is probably the most random we have. That's a point set generated by a Poisson point process on the left. And on the right is a perfectly periodic lattice, C2. And I want to convince you in this talk that, of course, what probabilists love on the left-hand side, looking at point processes and so on, there is a way of randomizing a lattice, and in fact, such random lattices have beautiful distributions that appear somewhere in the real world. So in order to warm up, let me just work in one dimension and remind you what a Poisson point process is. So you can think of a Poisson point process as events on the real line. You think of time. And each of those elements in the sequence psi n are random variables, and their joint distribution is determined by the Poisson distribution. So first of all, the probability that you find k points in a test set R. So there's already the first typo. This should be k points are equal to k. So the number of n of our infinite sequence that falls in here is given by this famous Poisson distribution where the length of, or the measure of the set appears and the number k. And furthermore, if you look at disjoint test sets B, B1 and B2, then these will be independent. So that's a way of characterizing the Poisson distribution. And so now that's all fine, and you know this certainly is one of the distributions that have many applications in statistics, probability theory, and in science in general. Now, how do we define a random lattice in 1 dimension? So what we want is we want to fix the number of the sort of the intensity of our point process. So if we look at the number of points in a very large interval, we want that to be proportional to the size of the interval. So the best thing to do here is just to start with the lattice Z, right? Because that has sort of unit density. And so how can we randomize such an object? Well, the only sort of natural way is to shift it back and forth, right? And if you shift a lattice, after you've shifted by 1, you get the same lattice back. So this parameter, the shift parameter, which are called alpha here, is naturally parametrized by 0, 1, because once you move from alpha equals 0 to alpha equal 1, you get the same thing back. So you have a periodicity there, right? And then you can say, well, okay, let me now take alpha to be random, yeah? And so you get a random set, you get a random lattice. Now you say, well, probabilists, this is nothing random, right? And you're probably right, this is a very deterministic object. The randomness is only in this one parameter alpha. But nevertheless, you can ask the same question. What's the probability that the number of points in a test set B is equal to K? And let's take B to be an interval now. If you do that, you can work out that that probability is given by that formula. So that's already, you know, a non-trivial formula. But that's just because you look at a very specific question, very specific probability. But nevertheless, you have a point process. You know, point process is essentially a random set. That's how you can think about it. So there we have 2 examples in 1 dimension. One is the Poisson point process, and one is a randomly shifted lattice C2. Okay, now the way you can see that really we haven't got much randomness in our shifted lattice is if you, for instance, look at the gap distribution. That's something I'm going to return to. So the distribution of gaps for a Poisson point process is the exponential distribution. That's the famous waiting time, Poisson waiting time. So for instance, if you think of radioactive decay, which is completely random, we think, yeah, then the time between decay events, so if you listen to your Geiger counter, is exponentially distributed. However, if you look at the gap distribution for my randomly shifted lattice, it's always 1, right? Because actually it is complete rigidity. So it's a bit boring, but that was just a warm-up. And let's go to higher dimensions. So I'm going to go to 2 dimensions and mostly stay in 2 dimensions, even though a big part of my work is to actually look at these things in higher dimensions. But I think I can already explain to you the main features and the sort of exciting ingredients here in the 2-dimensional case. So first of all, I get a stiff neck down here. It's like sitting in the cinema in the first row. So I might come up in a minute. So let's construct a 2-dimensional random lattice. Now, if we want to do that, we have more interesting transformation available, maybe linear transformations. Of course, I could do the same thing as before. I have Z2 and then I shift it sort of randomly, and we're going to do that as well. But let's just apply linear transformations. So here I'm thinking of a matrix, and I think of X as being a row vector. So I'm multiplying from the right here, just linear transformations. And so we could now look at all orientation area preserving linear maps, so determinant is 1, and generate random lattices in this way. For example, you could shear your lattice randomly, right? So you start with Z2, you apply this unipotent matrix, and that just shears your lattice. And you see, when you shear your lattice, you again have periodicity, right? So when you start with u equal to 0, and once u becomes 1, you have the old lattice back, because it's an integer matrix, and so it preserves the lattice. So you have natural periodicity, or you can say, okay, I take U to be random, uniformly distributed in 0, 1, and I have a random lattice. That's a good thing. You can also rotate it randomly, yeah, is another option. And so you get a lattice that's rotated randomly. Fair enough. You still say it's boring, and I see a lot of bored people in this room, but it will get more exciting, I hope. So what else can we do? Well, let's remember how we can write general linear transformation. You can decompose any element in SL2R. So SL2R here still simply stands for the special linear group. So group of 2 by 2 matrices, real coefficients and determinant 1. So you can uniquely decompose it in this way, with U being real, V positive, and phi in 0, 2 pi. And then you can define a random lattice where you simply throw those 3 parameters at random. And we've already discovered that there's periodicity here in U, so it's natural to say U is random in the unit interval, and also we can throw phi at random. It's only in minus pi over 2 pi over 2, so not the full circle, because you realize that when you go from 0 to pi, for example, or from minus pi over 2 to pi over 2, you could just get minus the identity matrix, which you can commute through, and minus the identity matrix preserves the lattice C2, right? So you actually haven't changed the lattice. So that's, even though you get a different matrix, this is a natural way of parametrizing then your lattice. But what natural measure can we put on V? So V is sort of a positive half line, a positive number. Can we put a natural probability measure on V, right? And that's an interesting question, and I've seen some beautiful papers in the statistics literature in the 70s by some great probabilists, and they ask exactly this question. And what they weren't aware of is that there's actually a beautiful theory behind this, which I'll explain, which gives you a natural measure on V. But it's much more complicated than you think, maybe naively. Okay, now there is another question, of course. When you start with your favorite random lattice, like the randomly sheared or the randomly rotated, you could multiply a matrix epsilon here that's not random, and you could ask yourself, well, what happens if I look at the sequence of random lattices? Does it converge to anything, right? So now I'm talking about convergence and distribution, right? You have a random variable. In my case here, it's not a random variable, it's a random object. Does it have a limit distribution? And that's what I'm going to talk to you as well about, how you can prove limit theorems for such random objects. Okay, so my first step is to explain to you what is the natural measure to put on the V. And this is something that goes back to the beautiful work of Hermann Minkowski, well over 100 years ago now, 19th century, and others. Siegel, I mentioned that in a second. So this is, has its origin in the geometry of numbers. And I'm going to talk now even in general dimensions for general lattices in RD, in D dimensions. So here the relevant groups will be SLDR, D by D matrices with determinant 1 real coefficients. And this subgroup here will play a big role. This is simply the same group, just you now restrict the coefficients to be integers, still determinant 1. And then there is a beautiful way of parametrizing a general lattice. So again, you apply a matrix M from this group. So you deform your lattice by linear transformations in RD. And there's a very natural one-to-one correspondence between cosets of this form, where you take an element in SLDR and you mod out SLDZ, and a given lattice. Now, the reason why I mod out by gamma naught SLDZ is because it preserves ZD, right? So if you take a matrix M and you replace it by gamma M, you get the same lattice back. And in fact, that's the only obstruction you have here to establish this one-to-one correspondence, yeah? So the map from here is clear. You go from M, and that gives you a lattice. But if you want to now go back, you can only do this modulo SLDZ. Okay, perfect. So in other words, we now say we have a correspondence, one-to-one correspondence between this coset space here, G naught mod gamma, which is a homogeneous space. It's a D group modulo a discrete subgroup, closed subgroup, and the space of Euclidean lattices in RD of covolume 1. Now, why is this important? Well, it now gives us a very natural topology on the space of lattices because we have a homogeneous space, and it also suggests a very natural measure on this homogeneous space, and that's simply Haar measure on G modulo gamma. So you look at the cosets. So you start with a Haar measure, which is sort of the natural G invariant measure on G, and you mod out gamma naught. And what is the beautiful observation of Minkowski is that, in fact, the coset space has finite volume with respect to this measure. That's the big discovery. Yeah, so if you say take a fundamental domain of the group action of gamma naught on G, that's some set. If you measure it, it's finite.
In the example before, you said it's obvious for U and phi, that's not obvious. That's
the V comes in a minute. I'm going to explain to you how the V comes in. So right now I'm giving you a completely abstract definition, and then I'll explain how this is related to V.
But the fact that it's finite dimensional with respect to this metric, it was obvious. I mean, U and phi obviously.
Exactly, but it's not at all obvious whether it's finite measure with respect to V.
Yeah,
so I'll exactly, absolutely. So however here, in particular in D dimension, this is very sort of big statement, and it's a complicated calculation to actually prove this. So for now, I just want you to swallow and just say, okay, we now have the Haar measure gives finite mass to any fundamental domain of this gamma naught action on G. And I hope on my next slide I'm making the connection with the V, otherwise the punchline is gone. Or maybe it is gone. Before I hope, we'll wait for that slide. If there's no slide explaining the connection with V, I'll show you. Okay, so now you can work with this measure, and you can start proving various formulas. For example, you can say, okay, let me look at some interesting functions on the space of lattices. So this is, for instance, an interesting function where you take your favorite lattice and you sum over all lattice points in your favorite lattice. And you introduce some weight function. Think of f as some measurable function or just a compactly supported function, just some bump function, yeah? And so what this really does, it counts the number of lattice points that fall into the support of this compactly supported functions with a weight given by the function. Now you can say, okay, well, that's a function clearly on the space of lattices. It just depends on the lattice, right? So you can think of it as a function on the space of lattices now, the whole object, the whole sum. And you say, well, what is this average value? So if I now average over my normalized Haar probability measure, the one that I had on the previous slide, what's the answer? And the answer has been calculated by Siegel in a beautiful formula. The answer is, well, first of all, you get the value of the function at 0. That's obvious that there's a term like that because x equal to 0 is in here, yeah? And for that, you get f of 0, and then you just integrate, that's a constant, then you just integrate, it's independent of the lattice in particular, right? Every lattice has 0 in it. And then you integrate over it, so you get this term, because mu naught is normalized to be a probability measure. And then the important observation of Siegel is that when you integrate all the non-zero, the sum of the non-zero terms, you get this. You just get the Lebesgue integral of f. So that's a beautiful formula. It sort of says that if you average over the space of lattices, you get Lebesgue measure, this function. And Rogers calculated mean values of higher order correlation functions, but these are very, very complicated objects, but very interesting as well, and they have had a real resurgence of interest recently. But I'm not going to dwell on that. I want to now give you the answer with the V, because I think to my embarrassment, it's probably never going to appear on any of those slides. But the point is that when you are in SL2, let me see. When you're in SL2, as I explained before, there is a decomposition, a unique decomposition. So SL2 is clearly a three-dimensional Lie group. It has 4 parameters, but determinant 1, so 3. And this is a good parametrization. I've written this down before. That's where the V was and the U. And here you have your cos phi minus sin phi, cos phi. I think I've written it. I parameterize in this way. So this gives you a very nice three-dimensional parameterization, 3 good parameters for the group. And now the key thing is that here you can actually work out what the Haar measure is explicitly. Oh. DUV. Should I speak quiet, more quieter? And here there is a normalization constant, which I can't remember at the moment, but it's something like this. So this is actually the way Haar measure looks like in those coordinates. But now if I showed you this in the beginning, you would have said, but it's not normalized, right? The trick is that you're only allowed now to integrate over the fundamental domain. And in this case, and I show this later, I think I show all of this later, but anyway, the fundamental domain here looks like this. So so that's minus 1/2, that's 1/2, 0. So this is the complex upper half plane. And so U and V are parameterized here. So U is this direction, obviously, and this is V. And then the phi is just the circle coordinate. So you see, you put the back measure on the circle as before. On U ranges between 0 and 1, except if you're down here, and it's more complicated, right? So that's why it's actually very non-trivial. These things are not independent of each other because of the shape of the fundamental domain. Good. Now, and now we come back to the very first slide. We say, actually, we also want to have shifts. Yeah. So what I'm doing now is I'm not only applying linear transformations to my lattice, but I'm also shifting them.
Do that in linear. That's actually the highlight. Those fundamental domains become extremely complicated.
Yes. Absolutely. In fact, the shape of the fundamental domain is very, very complicated, and a lot of clever people have tried to find good, there's no unique fundamental domain, but you try to find those that are well adapted to your calculations, and I'll come back to that point. So you can say, I also want to shift my lattice, so you have a shift variable, which I now call Z here, and the natural thing is you define a new Lie group, an extension of SLDR as a semi-direct product with RD, which we here think of as a group of translations. And I don't want you to go through all these slides. My only message here is that you can define now a group that also includes translations, and you can define a homogeneous space, which is now simply G mod gamma, where the new arithmetic subgroup is again that where you replace the reals by integers. And now it's actually quite an easy exercise to show that this also carries a finite G invariant probability measure, which is simply the product measure of the original probability measure on SL2R, normalized to give mass 1 to the fundamental domain, and Lebesgue measure, because essentially what you get here is you get a fiber bundle of the original homogeneous space times a torus. And on the torus, you just have Lebesgue measure on which SLDZ acts. But forget it, yeah? I just have this here for completeness. So those who like this stuff, they can. And then what happens is that you, again, can prove analogs of Siegel's formula. In fact, here it becomes very easy to do because you only need the translations to prove this fact. Because of translation invariance, you already get this formula for free. And the Rogers-style formula with higher order correlations can actually be derived from Siegel's formula. So you now get identities of this form that are very beautiful and that are also very useful in the various applications. And there is a natural probabilistic interpretation. So if you remember, one of my motivations was to talk about random lattices and sell them to you as point processes. So if you really adapt that notion, and you now, for those of you who are probabilists, you can now formulate all of this in, of course, just probabilistic language. So what you would have here is your point set P summed over this particular test function, and you can think of this as actually a point mass that has a Dirac mass at every point in your point set, and you're really just testing it against your favorite compactly supported test function. If you take the expectation of that, by definition, it's the integral over your space, yeah? And what Siegel's formula tells you is that this is equal to the integral of f with respect to Lebesgue measure. So this formula actually, in the notion of in the sort of notion of point processes, says that the intensity measure, so this here defines the intensity measure, is given by Lebesgue measure. Okay, so the intensity measure is basically just the measure that you get when you take your point masses, mass 1 on each, and you take expectation value. And to make this real, you have to test it against the test function f. And you see on the right-hand side, it's dy, so it's just Lebesgue measure. So what this says is that Siegel's formula for random lattices states simply that the intensity measure of this random point set, random point process, is Lebesgue. And you can look at higher order correlation functions as well. So if you have a random affine lattice here, then as you've seen, the sort of second order formula gives you this, which is as well compatible with a Poisson point process. So if instead of P here being a random affine lattice, you would have P a Poisson point process, you would have exactly the same formulas. So for those first and second order statistics, my random affine lattice is indistinguishable from a Poisson point process. That's kind of interesting. It's actually more interesting than you think, because people have, statisticians, point process people, have looked at exactly this question. The thing is just they didn't think about random lattice until Olaf Kallenberg came in. That was the guy I mentioned earlier, who was sort of trying to understand random lattices, probability measures, and so on. And he wasn't quite aware of the Minkowski and Siegel theory that was developed in the number theory literature, and it was John Kingman who pointed that out to him.
Do you want to think that in some type of average sense, the diagonal contribution is negligible in the second?
Oh, I've just excluded the diagonal contribution, and the reason for this is if you look at the sum when x1 is equal to x2, you have x1, x2 here, it's actually the same object as up there. So I could have included it, but then I would have got another term plus integral just over y of f of y comma y, right? So you can reduce the diagonal to this formula. And that's the only reason why I've excluded it, because it's sort of a trivial term once you know the first line. And the same is true for Poisson point processes, right? So the diagonals are always trivial because they just correlate with each other. Okay, good. So now, as I said before, we actually are interested not just in these average values, correlation functions, so on. We actually want to understand the exact distributions, and that's really hard to work out. So if you ask me, can you tell me the probability when M is now, when this ZDM is now a random lattice or random affine lattice, as over here, can you tell me what this probability is? And I can't, except in some very special cases. So that's really a great challenge. And let me tell you, just to give you an illustration of one of those calculations that one can do here. And that's in the two-dimensional case, so d equal to 2. And what we want to work out here, and then later you'll see the reason why I'm focusing on this particular contribution. Well, the main reason is I can work it out, is the following scenario. So here we have, first of all, think of this as the basis of your lattice, right? So we look, I haven't shown you the lattice. So there's a lattice here in the background, and the lattice is basically all integer linear combinations of these two basis vectors, r and s. They are fixed. And as you move through your space of letters, you just move r and s around. And what we want to understand is the height of the vector in my lattice that falls into this strip. So there are many in there, infinitely many in general, but we want to understand the distribution of the vector with the lowest height. Yeah? So this one wouldn't qualify because it's not in the green strip, and this one as well, it wouldn't be in the green strip. If I would move my green strip to the right, then R would appear as the one with the lowest height, yeah? So that's the game. We fix the strip, that's parametrized by W, and now you just want to work out that quantity. Now R and S are random. The lattice is random, right? So we get a probability. And this is the measure that we have. So you can now ask yourself, well, if I start with a lattice Z2 times M, parameterized by these things, can you work out the probability distribution for the vector with the smallest height? Okay, you can, and this is the formula. It's sort of an elementary function, but you can already see from the formula that it's not a completely trivial thing to work out, but it can be done, right? And if you look at some of my papers, you'll find this there, you'll see also the reason why we looked at this. There was a motivation which had to do with statistical physics and with number theory problems, but I'll get to that in a second. So the theorem is the following. So if you look at a Z2M as a Haar random lattice, then the minimal height vector Q in the green strip is distributed according to this probability density here. So I'm actually saying more. I'm not just interested in the height of this vector. I'm actually telling you where this point is. Yeah. So the coordinates of this point is Q1, Q2. So that's the minimal height vector. The coordinates of the minimal height vector, which is a random variable, and it's distributed according to this density. Now this obviously depends on where my strip is. And just for fun and make the formula a bit easier, let's throw the strip as well at random, yeah? You're happy with that? So I'm just gonna now take V to be a random variable as well, and V is distributed minus a half. And again, that's fine because there's some reason of why I want to do that. I could have thrown it also in a bigger interval, yeah? Okay, cool. So that's that. And then you get this formula P of S, which looks nice. It has logs in it, and otherwise it's all very elementary. But again, you know, it's a calculation you have to do. You basically have to integrate over various domains that are restricted by the geometry that you have here.
And what is S?
S is now the...
Is the height?
S is now the height of... Exactly. S is the height of this vector. And the point is here, you see, once you, so this is a random variable. Yeah, that's a very good question. So Q is a random variable. Here I've given you the density. Now I integrate over V, and I've only, so Q2, that's the height coordinate, that's basically equal to S. So I should have kept it as S, yeah? And because I've averaged over W, I'm ignoring the horizontal coordinate.
You're not keeping track of that.
I'm not keeping track of that, yeah. So then you get this formula. So this is again a probability density, and it has two regions here, S less or equal to 1 and S greater than 1. And you see it looks it looks like this. It's the red curve here on this graph. Now, actually, we weren't the first to work out this probability PS. This was done in a heuristic paper by Dahlquist, who asked himself the question of what is the distribution of the free path lengths of a point particle that moves around in the so-called Lorentz gas. So the Lorentz gas is a very old model in statistical mechanics where originally Lorentz had in mind to model an electron cloud moving in a metal, and metal is modeled by scatterers. And you want to understand how does it move, in particular when the scatterers are very small. So the problem of the free path lengths is the sort of the first problem you want to understand there, which basically means you start somewhere here at this point and you shoot off in a random direction. You can even take that initial point to be random, and you ask yourself, well, what's the probability that I hit the first scatterer after time t? And when the radiuses become smaller and smaller of the scatterers, this time will become longer and longer, and you have to rescale, and you can try to work this out. So this is what Dahlquist did. And then Boca and Zaharescu actually proved this rigorously. So there was a few gaps in this heuristic argument. So Dahlquist was a physicist. But it was a very ingenious calculation, and the most impressive thing is he got the right formula. So that's already non-trivial, and using his heuristics. Boca, as I said, and Zaharescu made that rigorous using classic methods in analytic number theory, continued fractions, Klosterman sums, and so on. So what our contribution here was to actually realize that this distribution that you see there comes from a random lattice. So that was completely opaque in all previous works. People just did a calculation, right? They measured the length and averaged and got something. But the fact that there is a random lattice with respect to Haar measure underlying was not known. And so once we had that insight, we could generalize all this work to higher dimensions, because as you know, as you appreciate, in higher dimensions, a lot is more complicated.
So would that random lattice be a subset of this, just where you have just rotations?
No, no, no.
It's not.
It's not,
Okay.
and I'll show you in a minute. So the limit distribution, the red curve here, is actually the Haar measure on the space of lattices. But you're right, when you start with a problem, you just shoot off in a random direction, so you just have rotations. But I'll reveal that mystery. So that's good. So here you have, and I think it's quite remarkable, there's a beautiful limit distribution that comes out in a very natural problem in statistical mechanics. So that's number one. Number two, here's another example. So in quantum mechanics, as some of you may know, the big discovery of quantum mechanics is that if you have quantum systems that are bound, for instance, a hydrogen atom, well, not all of the hydrogen atom, but in particular harmonic oscillators that swing backwards and forwards, the energy levels are quantized, so they form a discrete subset of the real line. And you can ask, for example, what about the distribution of the gaps between consecutive energy levels in such a quantum system? So the quantum harmonic oscillator is clearly one of the fundamental examples, and the energy values look like this. So parameterized by two integers, M and N run through all natural numbers. W1, W2 are the frequencies of the harmonic oscillator. And then Greenman found out that when you look at the gap distribution, it looks like this. The red curve, it's the same red curve that we had on the previous slide. And indeed, the two distributions look the same. And what is kind of remarkable that in the literature, no one made this connection. The two formulas are explicit, but you know, they look a bit complicated, and maybe you have slightly different normalizations. So no one actually said, hey, we've got the same limit distribution for the gap distribution between energy levels of a harmonic oscillator and the free path length distribution of a of the periodic Lorentz gas. And I've happened to have worked on both problems, and when you have the interpretation of the random lattice, it's immediately obvious why the two things should be the same. And I'm just going to illustrate that to you. Now, of course, it's obvious when you look at the formulas, but as I said, you need to compare formulas. But once you have the setting of random lattices, you just see it. You don't even have to make a single calculation. It's not quite as trivial as that. So let me explain. So as I said earlier, all the previous rigorous works used methods from analytic number theory, continual fractions, etc. Our theorem works as follows. So as you said earlier, when you start with a problem and you shoot off your particle in the Lorentz gas in a random direction, you basically put a measure on the directions, which in two-dimensional is just a measure on the circle or on the rotation group, right? Now, instead of rotating your initial condition, you can fix your initial condition of the particle and rotate the lattice. So there you have a randomly rotated lattice, the one that I started off with. But also, when you make your scatterer small and you understand how the various length units work, you actually realize that what you're really looking at after that additional natural rescaling is a question of a randomly rotated lattice that's then stretched by this diagonal matrix. And what one can show is that in distribution, this sequence, parametrized by epsilon, of randomly rotated lattices converges to our favorite random lattice with respect to, where M is distributed with respect to Haar measure. On the other hand, if you look at the gap distribution of this quantum harmonic oscillator, of its energy spectrum, then you apply a random shear. I can't explain you all the details, right? But that's what's coming out. You're actually looking at a randomly sheared lattice, again, stretched by this matrix, epsilon 0, 0, epsilon to the minus 1. And now, by the beauty of ergodic theory, this also converges to the same random measure in the limit, right? And if you look at the problem, the test sets that you look at for the gap distribution and the free path lengths are actually just rectangles. And that's why, same test set, same limit, that's why the two problems have the same limit distribution. They don't have the same value for any finite epsilon, because one is a shear, the other is a rotation, but in the limit they do. So once you have established this convergence here, which is of course a much more general fact, has nothing to do with the problem that you looked at, then you see the answer immediately. You don't even need to do a calculation. Yeah? So you don't need to compare these relatively complicated formulas. So that's my main message. And now how do you prove those convergence of the random lattices? Well, you remember, what you have to do is you have to remember now the correspondence of the space of lattices with this coset space, which in turn can be identified with a unitangent bundle of the upper half plane, modulo SL2Z, so that's the modular surface, because remember, U plus IV was really parametrizing, two parameters of SLDR, and these are actually the parameters on the upper half plane, and phi is just the direction of a unitangent vector. And so you get this correspondence, and then you can apply classic equidistribution theorems that actually show us that large circles in this space, so this really parametrizes a large circle, and I've drawn a picture here of how this looks like. This is actually a large horocycle. So the shear corresponds to parametrizing a horocycle, and we know that these things become uniformly distributed. And once we know that these large horocycles or large circles become uniformly distributed in that homogeneous space, then one can, again, you have to do something, but you can use sort of a continuous mapping theorem to then show that in the right topology on the space of lattices, the lattice also converges in distribution to the limiting Haar measure. So that's the idea. And lots of people have worked on this. One can make it effective. It's really one of the cornerstones. Yeah, here's a longer one, and you can already see sort of the density of where this limit is sitting, yes? And you see very nicely here the 1 over V squared. So the smaller V is, the higher the density goes. And that's really, you see really Haar measure emerging here in this picture. Okay. And now, well, once you have the limit distribution, you can then ask yourself, well, can I work it out? And as I said, it's very difficult to work this out in higher dimensions. In fact, we can't do it. So even the free path lengths for the Lorentz gas in 3 or more dimensions, we don't have closed formulas. But we can, for example, prove that it has a heavy tail. It decays like s to the minus 3. So P of s is now the probability density for having a free path length at S, yeah, and so this is, oops, sorry, this is the distribution, and we can do more and more. We can also look at quasi-crystals. So our theory has then been developed by us to prove analogous statements for other point sets.
What's the intuition of this limit of epsilon itself?
What the intuition is?
Yeah.
So I've not really explained to you why this stretch by epsilon, by this diagonal matrix parametrized by epsilon, is related to the problem.
Right.
That's would be another talk. So, and I can explain it to you. It's actually not so hard. But that was actually the main discovery.
Yeah,
that was the main key point. Yeah. So I can explain it to you afterwards if you're interested. And this was more like a whole roundup of the various things that can happen. So I have another 2 minutes, correct? And what I wanted to do in those last 2 minutes, probably would have been the last 10 minutes, is just to show you some other distributions that come from the space of lattices. One is when you look at the gaps between a sequence like this, n to the beta mod 1, and where n just runs through, 1, 2, 3, 4, all the integers. So you take fractional parts of this, you order it on the unit circle, and then you, like for the harmonic oscillator energy levels, you ask what's the distribution of gaps. And there, in a beautiful paper by Elkes and Kurt McMullen, Noam Elkes and Kurt McMullen, almost 20 years ago, they showed that there is a limit distribution for this gap distribution that looks like this. And you already see that this looks very familiar. It's not exactly the distribution I've showed you before. It's a relatively close brother or sister of this other distribution, but it's not exactly the same. So this comes out. What's interesting is that this only works when beta is equal to 1/2. You get this distribution. For all other values of beta, strictly less than 1, you get an exponential distribution. So it seems that n to the beta is actually like a Poisson point process, certainly for the gap distribution, but people have done other tests, which is really amazing. I wouldn't have expected that. But when beta is 1/2, there is some symmetry underlying that leads us to the space of lattices. And that's what Elkes and McMullen discovered. So that's another example. And we discovered when we looked at this problem of the Lorentz gas, that you can also just look at the directions of lattice points and ask for the gap distribution there. And by another magic coincidence, you get the same distribution as Elkes and McMullen. And it's again the same idea that, well, if you look at the formulas, they're clearly the same, but the real deep reason of why they're the same is the ergodic theoretic observation that different averages converge to the same limit. And as I said, we've also looked at distributions of directions in quasi-crystals where people numerically observed.
In this case, it's obvious that the harmonic theory goes to 1/2. The random lattice, it seems absolutely not obvious.
It's not obvious at all, but it becomes obvious once you read the paper, and then you discover this underlying symmetry. It's absolutely non-trivial. It's not a one line. It's an approximate argument. It's very delicate. But once you see it, it comes out quite naturally. Anyway, so if anyone here is interested in quasi-crystals, you can do the same thing. You can sit somewhere in your quasi-crystal and you can look at the directions of all points in your quasi-crystal inside a big ball of radius t, and you say, well, what is the gap distribution? Does this have a limit distribution as you take more and more points into account? And, you know, in this paper, there were some numerical studies, and you see limit distributions come up, and you, again, see something that looks a bit familiar. And indeed, you can show that also for quasi-crystals that come from so-called cut and project sets, one can actually establish this rigorously. One of my big dreams is to also do this for quasi-crystals that don't come from cut and project sets, but I'm not going to go into detail. So if you don't know what these terms mean, ignore it. And now you can play the same game in hyperbolic geometry. You know, so far we've just looked at random lattices in the Euclidean plane or Euclidean space. You can do this in hyperbolic geometry. So here is a picture of Escher that I think many of you have probably seen already, and you could say, well, I can generate a lattice by, for instance, just starting with this eye of this kite and look at its images. That gives me a hyperbolic lattice points, yeah? And can I randomize those? Well, yes, one can, but in the interest of time, I won't bother you with this too much. All I want to say is you can apply a very similar machinery and you see distributions like that. And I hope that's given you a little bit of an insight on what one can do here. I really wanted to talk to you. I know Igor would have liked to see this more, but you've already heard me talk about that, Igor, I think. Where actually you have some number theory problems, like this one, that I won't discuss in detail, of the solutions of quadratic congruences. And so for each m here, d is fixed. For each m, you get finitely many solutions, but you can look at the sequence of solutions that you get for every m. This defines a sequence modulo d. You can, modulo m. You can normalize by m, and you get a sequence of points in the unit interval, and you can say, what is the gap distribution, for example? And what we found is that we could use, again, the notion of random hyperbolic lattices to explain this limiting gap distribution. And I'm just showing you the pictures here and the theorem. I haven't shown you here a red curve. This curve is just the exponential distribution, which you would get for random points. Depending on d, you get different distributions, and we, in principle, have a formula. It's just very complicated to work this out. So this is the gaps you get between solutions of quadratic congruences, roots of quadratic congruences, normalized appropriately for different d. And trust me, what's underlying here are random hyperbolic lattices distributed according to Haar measure. Yeah? And the reason why these curves look a bit complicated is just simply because the test functions we evaluate over this random lattice is a complicated function. Good, so this is the so-called pair correlation function. I'm just showing this because here we could calculate the red curve, which agrees with the sort of numerical experiment, and it better should because it's a theorem. And now I'm just going to flick to the end and give you some reference if you want to have some bedtime reading. I think these are nice introductions to the space of lattices, and in this LMS newsletter article, you'll find the comparison between the harmonic oscillator and the free path length distribution. This American Math Monthly is a little account of how the three-gap theorem can be proved using the space of lattices, and that, one of the pictures I had there was from this paper. So I hope I've given you a little panorama of the fact that although when you start with a random lattice, it seems not at all like something that is really random, but it produces beautiful limit distributions that in turn come up from natural questions that people have asked. Yeah? So it's not that you just define your distribution and you find the problem. These questions were there, and they can be very naturally and transparently answered through the space of lattices. And using some very powerful ergodic theory, which I completely ignored here. So the machinery behind proving those limit theorems is very involved, and I've showed you one slide with names of many famous people. But for instance, for the quasi-crystal, we use Ratner's theorem, Marina Ratner, one of, to me, the biggest discovery, certainly in ergodic theory in the second half of the 20th century. Great. Okay. So thank you very much.
So for the random hyperbolic lattices, is there such a simple description for this case as an Euclidean case?
Yeah, so it is quite similar, and without going into the details, in fact, the Euclidean case can be thought of part of the hyperbolic case by just mapping. There is a map from the Euclidean plane to the real plane. So here you take a discrete subgroup again of your Fuchsian group. You take SL2R and you take a discrete subgroup, i.e., a Fuchsian subgroup of finite volume. So before we had SL2R and SL2Z, but you can take something much more general. And then you say, well, what is now a hyperbolic lattice? Well, you just take a favorite point in the upper half plane and you look at its images under gamma, right? So before, you can think we start with the origin in the Euclidean plane and then we just look at the images under all integer translations. Here's the same thing, except that instead of integer translations, we look at the isometric action of my Fuchsian group on this point B, and that gives you a fixed thing. Now you can say, well, what do I randomize now? And the right way of randomizing is now to multiply from the left with a random element in SL2R, right? Which is now, because again, if you replace G by G times gamma, you get the same thing. This is naturally parametrized by the right coset, G modulo gamma. And so that's your random lattice, random hyperbolic lattice.
In fact, what I was referring to is more to the explicit description than this.
Ah, okay, yeah. Yeah.
Is there any more about that?
So in terms of limit distributions?
No. So you had a very explicit description in this parameter B. Theta was it 5? And you, if I remember?
Yeah, you mean this here?
Yes.
Yeah, so we're still in SL2R. So what is different now is simply that you have a more general Fuchsian group modding out on the left. So you left to, you might have a different fundamental domain. So the Haar measure is still the same. But the problem is, when you then want to calculate probabilities, you need the form of the fundamental domain, which is fine. But then also you have a certain test set in which you want to count. And that's where it becomes quite complicated. It's really only integration, but we all know that integration can be difficult. Depends on the domains. Yeah, so it's still very explicit. Mm-hmm.
So in some sense here, compared to the classic case, you're replacing your z squared by gamma, and then you're establishing over different settings. Is it interesting from your perspective to also consider like the different gammas or different gammas? So,
yeah, absolutely. So you, of course, here when you take G times gamma, you can also think of conjugating gamma just by a G, right? But that's still essentially the same problem. There are other interesting things what one can do, but I haven't looked into that by taking a hyperbolic surface and then moving in Teichmüller space. I mean, that's what Mirzakhani worked on. So there's a natural way of thinking about a random hyperbolic surface in Teichmüller space, and there's some beautiful work going on at the moment, in particular for large genus, where you can actually derive nice formulas. So that's another direction which I think is really exciting.
I was wondering the results that you say you have for the quasi-crystals.
Mm-hmm.
Is that are those obtained by using this projective embedding of a proper lattice, regular lattice into from higher dimension.
Yes, exactly. So in where we can do things is when your quasi-crystal is generated as a cut and project set. So it means you start with a high dimensional lattice, say a 5-dimensional lattice, and you define a slab in it, and you select all the lattice points in this slab, and then you project them down to your 2-dimensional plane. And then you see what will happen then is we're working with SL5R with an SL2R action. So we still only rotate in that 2-dimensional plane, and we only stretch in that 2-dimensional plane, and that's where we actually need Ratner's theorem, because we now work in a very large dimensional space, and the equidistribution is much, much more difficult, much more subtle. Yeah, exactly, yeah.
Any other questions? Again, thanks, Jens, once again.